In this video, we'll see the approach known as unsupervised pre-training for improving the training of deep neural networks. So we talked before that there are two reasons why we can observe that training deep neural networks is hard. One, which is related to underfitting, which might require to use better optimization methods. And finally, a second possibility, which is more associated with overfitting, where we'd use better regularization. And so here, what we'll see is one approach based on the incorporation of unsupervised learning as one approach for addressing this second hypothesis for why deep learning is hard. So the solution is actually fairly simple given what we've seen so far. The idea is just to change how we initialize the parameters of the hidden layers. And specifically, we're going to use unsupervised learning to initialize the parameters of the hidden units in the hidden layers. The idea here is that we want the neural network to not just extract features or representation, which is used for classification, but also extract hidden units that also extract more information about what the specificities of the input distribution. And in particular, we want to encourage neural networks that can represent this latent structure that's specific to the input distribution on which we're training. So for instance, if we're training on images of characters, then we'd like hidden units to contain information for why this is a character image and that this is different from data that would have been generated from any other distribution, such as a random distribution where each pixel is uniform, so which would generate this, something like this, like a random image. So we want to add this regularization that says amongst all neural networks that do well on classification, I'd like to favor neural networks that also understand why my input data is special and is different from, say, random data. And that's essentially what unsupervised learning is trying to do. We've justified restricted Boltzmann machines or autoencoders as training to sort of make that distinction in some way. And so now we'll try to encourage our deep neural network that do classification to also try to do this to some extent. And so now we're asking a bit more about our neural network. We're not just asking it to be good at supervised learning and classification, also asking it to learn what makes the input data special. So this should reduce the variance of our estimating procedure, and because of that, we should reduce the variance and thus reduce overfitting. And by doing this, we also hope that we're not increasing the bias too much. And indeed, in practice, often that's what we observe, in the sense that we do observe improved generalization performance by incorporating this unsupervised learning idea. The specific procedure we'll use for doing this, which is very common, you could incorporate unsupervised learning in some other way, but the procedure that's perhaps most popular and quite simple is known as greedy layer-wise pre-training. And so the way this is going to work is that we'll effectively add hidden layers one at a time, and then whenever we're adding a new hidden layer, we're going to train its parameters locally using an unsupervised learning algorithm for a single layer. And so for instance, we could start with this neural network here, where we just added our first hidden layer, and then we'll pre-train or train these connections here based on some unsupervised learning algorithm like an RBM, contrastive divergence algorithm, or denoising autoencoder, regular autoencoder, and so on. Then we do this from some iterations, then we stop, and then we fix these parameters. So this is illustrated by having these grayed out. And now we add say a second hidden layer, and then we train this hidden layer using, again, an unsupervised learning algorithm, like an RBM learning algorithm. But we train only that hidden layer on top of the data represented through the representation of the first hidden layer, which is extracted by using these parameters that we pre-trained before. So in other words, we're training, say, an RBM just on the same training set, but that's been pre-processed by this first hidden layer. and we do this for a certain number of iterations, and then we continue like this for as many hidden layers as we want. So we could pre-train then a third hidden layer, which is trained on the representation extracted by these two subsequent hidden layers. So we train on the data represented by this hidden layer, and so on for as many hidden layers we want. So in a nutshell, we train layers one at a time using some unsupervised objective. Whenever we're training a hidden layer, we're fixing the parameters of the previous hidden layers that have been pre-trained. And so we can view these other hidden layers, these previous hidden layers, as just feature extractors that provide an input representation for the unsupervised learning algorithm that we run for the current hidden layer. So yeah, this procedure is known as unsupervised pre-training. If you read that in the literature, that's what we're making a reference to. So intuitively, the first hidden layer will learn hidden unit features that are characteristic or more common in the inputs in our training set than, say, in random inputs or any other types of inputs. And then the second layer would learn combinations of first hidden layer unit features that are more common in the training set. Examples than, say, in random first hidden layer unit features. And then third layer would learn combinations of combinations and so on. And now the hope is that this initialization procedure, this pre-training procedure, will initialize the neural network in a region of parameter space where the local optima we will reach when we're doing subsequent backpropagation will overfit less. We correspond to a configuration that will yield less overfitting than if we had initialized in the random neural network parameter configuration. So like I just said, after this, after unsupervised pre-training, we just do regular backpropagation. This is often referred to as fine-tuning. So once we've trained, say, our first hidden layer, and then the second, and then the third one, we add an output layer, and we train the whole neural network using supervised learning backpropagation, so regular backpropagation in the feed-forward neural network. So again, we call this procedure often, we refer to it as fine-tuning. The idea, so the reason for that being that the parameters are, most of them are pretty much all trained really. They're not going to move that much. They're going to move somewhat, but not as much as, say, if we started from random initialization. So really the parameters are tuned for the supervised task at hand. And so in other words, the representation is going to be adjusted to be more discriminative for the particular classification problem I'm interested in. One nice feature of this unsupervised pre-training followed by fine-tuning is that if we have a lot of unlabeled data, we could do pre-training on more data than we do fine-tuning or backpropagation where we need labeled data. And so another sort of advantage we get from this procedure is that if we have not a lot of supervised data, labeled data, with a lot of unlabeled data, then we can get improvements by doing pre-training on the big amount of unlabeled data and then fine-tuning only on the small training set with supervised data. So here's just a pseudocode to perhaps make everything a bit more precise about what I just said. So the pre-training part iterates from the first hidden layer to the last. We build an unsupervised training set. That is, we take all of our training inputs and we ignore the labels if it was available. And then we compute the representation at the previous hidden layer. So for L equals 1, H0 is just going to be the actual input, the raw input. And then for L equals, so that's for L equals 1. For L equals 2, then we'd be computing H1 of XT here. So we construct this unsupervised training set. We feed it to what we sometimes call a greedy module. So that's just an unsupervised learning algorithm that can be trained, that trains a single hidden layer based on the representation that we compute here. So it could be an RBM or an autoencoder learning algorithm. And then we use the hidden layer weights and biases of that greedy module, that RBM or that autoencoder we train on that data set, to initialize the parameters for the Elliott hidden layer in our deep neural network we'll want to fine tune once we pre-train all hidden layers. Then once all hidden layers are pre-trained, we add connections to an output layer. So that's W capital L plus 1 and B capital L plus 1. We can initialize them randomly as usual. And then fine-tuning is just supervised learning using backpropagation with, say, stochastic gradient descent. All right, so that's unsupervised pre-training for learning deep neural networks. Now, you might wonder what kind of unsupervised learning algorithm you could be using. Historically, this unsupervised pre-training procedure was invented and proposed in these papers by Jeff Hinton and his colleagues. And that's where they suggested using RBMs. There was a whole rationale for why RBMs were the right algorithm to use for doing pre-training. But then later on, different people, including myself, proposed to instead stack autoencoders instead of stacking RBMs. So in the paper I was involved in, we proposed autoencoders, and in this other paper by people at NYU, including Marco Aurelio Renzato and Yann Lequin, sparse autoencoders were instead proposed. But essentially, the idea was very similar. The algorithms were different, but we were in both cases suggesting that we use another algorithm than restricted Boltzmann machine for initializing a deep neural network. Then later on, denoising autoencoders were proposed. They were actually proposed in that context, the context of training deep neural networks, and not just for extracting features in general. And there's been also a lot of other papers suggesting other types of unsupervised learning for pre-training. So there's an example here using the idea of semi-supervised embeddings or kernel PCA or independent subspace analysis. Again, in all cases showing that there were some gains from doing this, from stacking these modules of unsupervised learning. And so there's been a lot of research, and pretty much every time we'd see that unsupervised learning was being helpful. So this essentially confirms that it's really the general idea of unsupervised learning for initializing the parameters of a deep neural network that works well. And the choice of the learning algorithm will make some difference, but really the main characteristic that they all share is that they're unsupervised learning algorithms.